Hi everyone, my name is Justice and welcome to my TED Talk. I'm the co-founder and CTO of Metastable Labs and we are building the very first margin layer to prediction markets. Before this, I worked as a senior software engineer at Paystack, and for context, Paystack is like the biggest payments company in the whole of Africa, and just a few years back, it was acquired by Stripe. So at Paystack, I spent years building and operating systems that processed hundreds of millions of dollars in transactions every single month. So it's safe to say that I've been on both sides of the story, building features that look great in staging and then watching production teach you lessons you didn't ask for. So today I'm going to talk about what actually breaks in high traffic systems, why it breaks, and the technical habits that keep things running when things go wrong. And I'll try my best not to bore you guys, and I'll try not to make this a shopping list. Actually, I'm not going to make it a shopping list. So I'm going to talk about failure mechanisms because those are like the same whether you are on AWS or GCP or whatever. So the promise of reliability. So let's start with a simple truth. Most outages don't begin with chaos. They begin quietly. And the problem is teams or engineers usually look for chaos. They expect an outage to say stuff like service went down or 500 errors everywhere or their terminal all in red. But real incidents at scale start slowly, right? So they often look like requests still succeed, but on a slower pace. Your queues slowly grow and timeouts creep up. And while all these things are happening, your metrics still look okay, right? And then suddenly everything collapses. So the real question isn't how do we prevent all these failures? The real question is how do we keep the system stable while it is failing? So let me tell you guys like a realistic example. Let's assume it's a normal day at work, right? Traffic increases. Maybe you guys launched a new feature. Maybe it could be a marketing campaign, whatever it was. So everything looks fine for the first 20 minutes. Then one dependency starts slowing down. So it could be Postgres under heavier read or write operations. It could be your Redis getting hot. It might even be a third-party provider with limiting you because of all this whole new traffic. You get one API request, for instance. It calls service A calls your DB, which is Postgres. And then after that, it calls service B. Service B calls another service. Now, if one of these services gets slower, every other thing is affected. So your average query time grows from 15 milliseconds to about 150 milliseconds. So everything still works, don't get me wrong, and it won't feel like a disaster yet until you actually do the math. In modern systems, one user action can trigger multiple calls. Example, if a user loads the dashboard on the front end and it calls the back end, which in turn calls 6 internal tools, for instance, each of these tools or service hits the DB. And if one starts slowing down, it affects everything. So if you have, let's assume you make 6 calls, and each has about 100 milliseconds tail latency, you find out that your one request becomes 600 milliseconds very quickly. And believe me when I say this, tail latency is the real killer. Most teams look at average latency. Average is going to lie to you at scale, right? Average hides the real pain. So if P50 is 100 milliseconds, for example, but P99 is 5 seconds, users are going to feel that 5 seconds, not the 100 milliseconds. So if you do enough requests, someone is always living in that P99. Now, the system becomes increasingly slow. Developers then does what feels reasonable, they add retries. So what happens is the clients retries, the service retries, the SDK retries, everything attempts to retry. Now, instead of making one request, you are making two or three. And here is the trap. Retries don't reduce loads. Retries multiply load at the worst possible moment. And this is called a retry storm. So it turns slow dependency into a dependency death spiral. And this is how a quiet incident becomes a full outage. Next, you hit the next failure mode, which I call connection pool exhaustion. If Postgres if Postgres queries are slower, that means connections stay longer. And your pool quickly grows to 50 connections. Now, on normal conditions, requests complete fast and connections return quickly. But now, queries take about 10x longer, so those 50 connections are basically stuck. Now, you have incoming requests, right? But then they keep piling up because they are waiting for the last connection. So eventually, your service still looks up, but it's effectively frozen. Nothing works. Your CPU might look fine, your memory might even look fine, but your system is essentially now a zombie. So at this point, timeout starts firing. And this is where many systems are poorly designed. Example of a bad timeout behavior could look like it doesn't time out at all. So requests hang forever, or timeouts take too long, so you wait 30 seconds and block everything else. Or it could also be that timeouts don't cancel work at all. And this last one is huge. If you time out the request, but the expensive query keeps running, you have built a system that burns resources, doing work nobody needs. So now, users retry manually, right? Clients also retry. Services also try to retry as well. But all these retries are being caught. The DP instead is still doing work for already canceled requests. You get the point, right? So this is how systems die politely. No explosions, just slow suffocation. Slowly, the whole system dies. So when this is happening, let's be very clear. Your goal during an incident is not to do a root analysis to find out what's happening. Your goal first is to stabilize the system and protect users. So you want the system to shed loads, degrade gracefully, stop doing unnecessary work, and become stable. Only then do you try to find out what happened, right? So how do we actually do this? I'm going to walk you guys through some steps-to-step patterns that I use at work. The first step is to limit concurrency. High traffic systems fail when they accept infinite work. So one of the most underrated stability tools is this. We only process n number of these at a time. Simple. Make sure to limit concurrent requests per endpoint. You can limit concurrent DB queries and other stuff as well. So this is basically called a back pressure. It stops the system from melting itself. So it's better to return a 429 too many request, or even a quick please try again, than to accept everything and collapse. Because when you collapse, everyone just suffers. The next step is timeouts, but done properly. A good rule for this is timeouts should be short, consistent, and layered. Client timeouts might be 2 to 3 seconds for a user request. Service-to-service timeouts might be 500 milliseconds to maybe 1.5 seconds, depending on the endpoint. And here is the most important key. Timeouts must cancel work. If a request times out, stop doing any expensive work for it. Cancel all pending DB queries. Stop downstream calls. Basically, stop everything for that particular request. So this one habit prevents so many death spirals. Now, circuit breakers. A circuit breaker means if a dependency is failing or slow, stop calling it for a bit. This prevents your service from spending all its resources hammering something that won't recover. It also creates like recovery space, so we have some space to actually recover, right? If you do this right, you prevent cascading failure and protect your own service from being dragged down by a sick dependency. Now, the part that separates mature systems from fragile ones is graceful degradation. During such scenarios, some features should turn off automatically. Not everything is equally important. Example, in a payment infrastructure, we all agree that authentication is critical. Placing an order is also critical. But something like a recommended item widget somewhere is probably not. So knowing this, you should build the system to degrade. You could self-cache data or return partial results, or even turn off non-essential stuff. In payments, for instance, if your analytics pipeline is slow, you do not block payments. Instead, you degrade not the transaction. The next step is load shedding. This is being intentional about failure. You can shed load by rejecting the request early, dropping non-critical background tasks, sampling logs instead of logging everything. The line I always repeat all the time is, it's better to fail fast than to fail slowly, because slow failure destroys your system. Fast failure keeps you alive. And this essentially completes the list of things I feel you need to do. Next is things to watch out for. So most teams have monitoring, but in incidents, they don't know what matters. In a high traffic system, for instance, you need to track 4 things like your life depends on it: latency, traffic, errors, and saturation. And for latency, you need to track percentiles, not averages. So you want to see P50, P95, P99, and for each of these, you need to see the error rates, the queue depth, the DB connection usage, the thread usage, the downstream call latency, and so on. Because incidents often show up first as saturation, not errors. And here is how quiet incidents show up. So let's assume P50 is stable. P95 creeps up a little bit, but then P99 spikes, right? So what happens is queue depth slowly grows, DB connections approach maximum limits, our retries also increase as well. Then suddenly everything breaks. And when this happens, the right alert shouldn't be, is the CPU high? The right alert should be, what's the burn rate of P99? What is the queue growth rate? What is the error budget burn? What's the DB connection pool? Like, is it nearing exhaustion? Mature teams alert on trends, not burn rates, not raw thresholds. So when things are failing, loss alone won't save you. You need to take one request and ask, where did this go? And I call that a distributed tracing, right? Even if you don't have full tracing, you should do the basic things, right? So you should know where, you should check for correlation IDs, structural logs, consistent timing, and so on. Then you can see, so instead of having like normal logs everywhere, you could actually see how long your API call took. How long did it take service A to get a response from the DB, right? Where exactly did your query get stuck? And so on. And this is how you move from panic to diagnose. So let me say something controversial. Many outages are not prolonged by bad code. They are prolonged by messy response. I've seen incidents where up to 5 engineers are deploying fixes, right? Nobody owns it. Nobody knows what changed. Every fix introduces a new variable. So here's a simple step-by-step playbook I feel like will work. I know will work. The first one is name an incident lead. So someone needs to be the coordinator. That's very important. The second one is freeze non-essential changes and stop random deployments. Thirdly, stabilize the system. You can do this by reducing load, disabling some features, stop retries, and so on. The fourth one, so you can attempt to restore services. You can do this by rolling back to a previous working version or working deployment. You can reduce the blast radius, for instance. And the fifth one is only after stability do you investigate the root cause. The goal is to make incidents boring, not exciting. If you want reliability, you don't start during the outage. You start before the outage. You design with failure in mind. That means independence. So when clients retry, your system must not double charge or double create or even double execute. And this means you should have queues for expensive work. Don't do heavy work in line in the same request, right? It also means bulkheads. One failing part shouldn't sink the entire ship. Separate pools and resources for critical parts. It also means rate limiting. You need to implement a rate limit to prevent your system from abuse and spikes. And I'm going to end with this. High traffic systems don't break because engineers are careless. They break because complexity compounds faster than intuition. And the most dangerous incidents are the quiet ones, the slow dependency, the creeping queues, the retry storm, and so on, until production becomes a fight, right? If you want your system to survive at scale, you must put hard limits on work, use timeouts that cancel, add circuit breakers, degrade gracefully, share load intentionally, and so on. Because production will eventually test every assumption you've made. And the goal isn't to avoid that test. The goal is to build systems that can take it, and recover without drama. And this is the end of my presentation. Thank you for listening. You can reach out to me on LinkedIn if you have any questions. Thank you.